Hello everyone, I figured that I would do this one video before I go to bed. Today we have a nice IChO exam, IChO 55, question 8, talks about Nazarov cyclization. So here it explains that Nazarov cyclization is an electrocyclic reaction which can either proceed with heat or light. And our first question asks us to draw the pi molecular orbitals that describe the Nazarov cyclization. Fill in the LUMO, fill in the electrons and mark the LUMO and the HOMO. Okay, so let's go. So right here, let's draw our Nazarov thing first. Here it is. So here we have 5 p orbitals, so we're gonna need 5 energy levels. So this will have 0 node, 1 node, 2 nodes, 3 nodes, and 4 nodes. These are number of nodes. So for 0 nodes on the psi1 will be, of course, all of the orbitals are in phase. So I'm way too lazy to draw the p orbitals, so I'm just gonna write down the sign then. So there will be no nodes, right? And for the second level, there will be 1 node. So a way to fit 1 node into this level will be doing something like this. So on this so on the third p orbital will be a non-bonding. Okay, so that's 1 node. And for psi3, which has 2 nodes, you just add another non-bonding p orbital, like so. And now you have 2 nodes. Then psi4, which has 3 nodes, you just kind of repeat the same thing, but just turn the plus sign so that it would be out of phase of each other. There you go, that's 3 nodes, 1, 2, 3. And for 5 nodes, you just alternate the pi orbitals. Sorry, not 5 nodes, 4 nodes, 1, 2, 3, 4. Good. Now, it's time to mark, it's time to fill in the electrons. Well, there is one question that you need to consider. Is this part of the pi system? Is the CO double bond part of the pi system? The electron in the double bond, is it part of the pi system? Now you can answer this by drawing the resonance structure. So the resonance structure of this will be something like this, right? And this carbon will be a positive charge. So as you can see, it is not part of our pi system, because as you can see right here, the electron in the double bond is mostly on oxygen. It's not delocalized in our pi system. So there will be only 4 electrons from these 2 double bonds. So there will be 4 electrons. So let's just fill it in. 1, 2, 1, 2. And then let's mark the HOMO and LUMO. So the HOMO will be, of course, the orbital with filled electrons. So that's going to be marked with an X. So I'm just going to cross that. And mark the LUMO. LUMO will be the first empty orbital. So sorry, not orbital, energy level. There you go. 8.2, from the pi molecular orbitals that you derive in 8.1, predict under which conditions the Nazarov reaction of the divinyl ketone will proceed in a disrotatory or conrotatory fashion. In the table, mark with an X conditions after which reaction is allowed. Now, electrocyclic reactions, electrocyclic or cyclic or whatever, electrocyclic reactions are always allowed. So it has to follow the Woodward-Hoffmann rules. Actually, it must be the Woodward-Hoffmann rules, right? Not the Hoffman. The Woodward-Hoffmann rules, which says that the number of the 4n plus 2 superfacial and the number of 4n antifacial components must add up to give an odd number. To give an odd number. So in this case, so when we consider our divinyl ketone, there's only one component, which is the divinyl ketone itself. There we don't have any other pi system that we can interact. The only pi system we have here is this compound itself. So it must have an odd number when you add all the components up. So it means that this system must be antiraphasial, because right here we have 4 electrons, right, in our pi system, because we have 2 double bonds. So this must be antiraphasial to make this reaction work, so that the Woodward-Hoffmann rules, so that it will obey the Woodward-Hoffmann rules. So when you draw an antiraphasial orbital, so it's going to be something like this, right? I'm just going to draw like that, and then you have the orbitals, right? Orbitals. So when you say antiraphasial, it means that the orbitals, they line up in a opposite lobe. So it's going to be something like this. Antara means opposite, so it's going to be something like this. This is antiraphasial, because right here the top lobe lines up with the bottom lobe, and this rotation method is called conrotatory. Because as you can see, the p orbitals right here, they rotate in the same direction, so it must be conrotatory. So when you do it thermally, this reaction will proceed conrotatory, and with photochemical, it will be the opposite, so it's going to be disrotatory. Good. Now 8.3, the Nazarov, I forgot to delete that. I attempted this problem before. Yeah. The Nazarov's reaction was used in a key reaction for synthesis of phthalate. For both conditions below, draw one possible structures of A and B, including stereochemistry. Note that the products of both reactions show a signal at that H NMR. So the Nazarov cyclization will form an alpha-beta unsaturated ketone. So, we have 2 conditions. This is a thermal condition, and this is the photochemical condition. So this will proceed conrotatory, just like what we said earlier. Conro, I'm just going to say conro, and this one is disrotatory. So conrotatory, you will have opposite stereochemistry, because you say you kind of twist the you twist. Let's say this is a substituent R, because you twist the orbitals in the same way. So this R group will be up like that, and this R group will point a bit down. So now it's on different faces. So the substituents will actually end up in a different manner, opposite to each other. So let me just copy this. So then I'm gonna paste it right there. Okay, now I actually got that. Okay, good. Now let's predict the product first, and then we can care about the stereochemistry later. So our product is just something like this, right? Nazarov that to give out this product. This product, because this carbon has a positive charge and this hydrogen will be eliminated, and then there you go. Okay, so here's our initial product. Now we need to determine its stereochemistry. Now we said earlier that for A it is a thermal, and it will do conrotatory, right? Thermal conrotatory. Okay, good. So the substituents of both ends right here will end up in a different position. So let me just draw that out first. I'm just draw that out. Now the official solution actually has 8 accepted answers, but you know, it really it is selective, but in theory it will give you 8 answers, but you know, they all counted as correct. So here's the skeleton, and this one right here. So the hydrogens, oh sorry, there's a methyl group right there. So this methyl group and this hydrogen will end up opposite to each other. So I'm just gonna say, I'm just gonna draw a wedge right there and a dash right there, and maybe a wedge on here too. But actually this one, they don't really care that much. You can draw a wedge or a dash right there, doesn't matter. But what matters is these two substituents. But I think this one is more of a wedge, because I think of this is on the same face as each other, so it's probably a wedge. So yeah. And then B, you have this rotatory, so it's gonna be the same stereochemistry, so we're gonna change it into a wedge right there. Easy peasy. Now 8.4. Now we have this scheme. The synthesis of capnoline commences with this, and then blah 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 blah. Choose the reagents on the list on the answer sheet that would be suitable as D. Now we need to find D. First step. So we have right here, we convert our carbonyl into a vinyl ketone. Convert our aldehyde to a vinyl ketone, and manganese 4 oxide, actually this one is an oxidizing agent, so it's going to oxidize something, and in this case it's going to oxidize our alcohol after a nucleophilic attack of D on the carbonyl. So D must be some kind of electrophile, and it must be a hard nucleophile, and D must be a hard nucleophile as well, because if D is a soft nucleophile, it would do conjugate attack. So we need to see what we have for D. So we have this Grignard reagent, we have a reducing reagent, and a vinyl lithium, which is really weird. Then we have a coupling reagent, some kind of coupling, and we have Gilman reagent. So of course the only hard nucleophile is the first choice. Great. Let me just delete all of this because it's messy. There you go. 8.5. Okay, just draw. Give the stereochemistry. Let's see. From E to F, P2O5 is this is treated in acidic conditions. This is a dehydrating reagent, so it's going to be a Nazarov, right? It's going to be a Nazarov. So we're just going to draw the Nazarov product. So it's going to be 2 cyclopentane rings together. Now, like so, and then 2 methyl groups right there. This double bond will be disappear. This double bond disappear, and then just gonna redraw and put this right down to there. It's gonna be like this. To give you, this will be a positive charge. No, that's way worse. It's actually going to be like this. There's a question of selectivity, and the question of selectivity is easily answered by the stability of the carbocation. If you drew the first product, which I have drawn earlier, it will give you a secondary carbocation. But if you drew it this way, it will give you a tertiary carbocation, which is undoubtedly way better. To give you right there. Great. So that's F, and then we know it's this rotatory, so it's gonna have some substituents and end up in different positions. Yeah. Okay. So it's going to be like this. Let me copy that. So that's going to be F So I'm just going to copy that to our answer sheet. Then G is just going to be a conjugate addition of F. We add a one methyl group. We add one methyl group there. And now we have to mark its stereochemistry, which we can easily just take it from the final product. So it's going to be something like this. Great. Then we treat it with an alkynyl lithium. So that's going to add to our carbonyl. But there's now a question of stereochemistry. So this question of stereochemistry can be answered as follows. Now, when you have a fused bicyclic ring, just like in this case, so the structure of the ring is actually going to be something similar like this. So we're going to have our five-membered ring like so. It's going to be something like this, like something similar to this. Now we also have H up here and methyl group right there. So it's going to be something like this. Something similar. Like, it's not accurate, but similar to something like this. And then we have our carbonyl right here, right? I think so. Yeah, okay. Now, the thing is, we have our lithium nucleophile, alkynyl lithium. Now, as you can see right here, this bottom face is kind of hindered because look at this carbon. Look at this ring part. It is covering the bottom face. This right here, it's covering the bottom face. So if you have a nucleophile and it's coming up from the bottom, it's going to be harder to attack. So an easier pathway is to come up the front right here, because the front, as you can see, it's way more open. So the alkynyl lithium will attack your carbonyl on the top face. So the final product, not final product, but H will have your alkynyl lithium, will have your alkyne attached to the front, to the upper face of the fused ring, and pushes down the hydroxyl group like so. So that's the fused ring stereochemistry. Let me find the what I noted down in here. Let me find it real quick. Cyclic system. Oh, sorry. Cyclic system. Fused ring. Where is it? As you can see, here it is. This is like some kind of a five-membered ring that is fused. As you can see right here, this face is way hindered. It's not open. Nucleophiles will have a harder time attacking down from the lower face because it's way harder for us to attack down here. So what's going to happen is it's going to attack on the front to give this stereoisomer. So your product IChO, let me copy that real quick. I also forgot to copy G actually. So your product H would be something like this, because the bottom face is way too hindered to be attacked by your nucleophile. Great. And then some rearrangement follows. Now then we continue and treat it with Grignard reagent over copper 1. So that will be transmetallation, and then a conjugate addition will follow. So I'm just going to copy this structure. And then J will be your final group right there, right? Because we did conjugate addition. And then your ketone right over here. And don't forget to indicate its stereochemistry. Now it's been given that both of these hydrogens are dashed. So I'm just going to draw it like that. Great. Now we treat it with what? Ozone over dimethyl sulfide. So that will change our alkene into a ketone or aldehyde or carbonyl. So it's going to be like so. Then we treat it with what? Potassium hydroxide. So that's just going to be aldol. So how it works is that this proton will be deprotonated, forming a nucleophilic carbon species, attacking this aldehyde to give you a 5-membered ring like so, with a hydroxyl coming out right here, E1CB mechanism, and then eliminates out the hydroxyl group. So that's just going to form our 5-membered ring. Like so. Then, for the last step, what do we treat it with? We treat it with, just hydrogen over platinum. So that's just going to reduce our double bond. Let me just copy this real quick. Like so. And then the last and final step is just okay, so the last and final step is just an addition of the methyl group to the carbonyl, changing the hydroxyl group into a chlorine, and then elimination follows. And yeah, that's it for today's problem. Thank you.